Okay, let's go ahead and get started. Hi, everyone, and thank you for joining us today. My name is Erin Otan, and I am Zpryme's Project and Campaign Manager. And I'd like to welcome you to today's webinar presented by Zpryme Networks, Distribution Grid Modernization, How Communication Networks Evolve to Meet New Demands. So before I hand things over to our moderator and panelists, I just want to let you know that we do want you to ask questions during the webinar today, and you can use the little Q&A box in the bottom right-hand corner of the WebEx window to submit your questions. And then at the end of the webinar, we'll take some time to have our speakers answer as many questions as we have time for. If you have any trouble with audio or video, just try refreshing WebEx or even closing out and signing back in will most likely help. And the slides and the webinar recording will be available after the webinar is complete, so don't worry about missing anything. We'll have the slides up on our site in the next day or two, and you'll receive an email linking you to both the slide deck and the webinar playback. Okay, so now we can get to what you all came for. I'm going to turn things over to Christine Richards, Zpryme's Chief Content Officer and today's moderator, to give you an overview of some Zpryme research.
All right, thanks, Erin. Again, my name is Christine Richards, and I'm Zpryme's research lead. So, again, we'd love to welcome you to the webinar, and we're really excited to have you join us today. So today we're going to talk about the evolving communication networks that can help with grid modernization efforts. All these physical assets of the energy industry, they continue to become increasingly connected, really to help enable things like automation, microgrids, renewable energy, and even things that go much broader into things like smarter cities. And as a result, what we're seeing is utilities really need solutions that allow this growing number of smart devices and sensors to be able to effectively communicate not only with the utility, but ultimately with one another, really being able to enable better operational as well as business decisions within their utility organization. Now, we're excited today to have a couple of great individuals with us to really help us consider these areas. I'm going to take a little bit of time here at the beginning to run through some research Zpryme is currently conducting to really explore the evolving world of communication networks in utilities. And then we'll have Matt Smith, who's the Senior Director of Grid Management from Zpryme Networks, join us and talk a little bit more about what's going on at their organizations with communication networks. And then we'll have Fermin Almeida, who's an analyst with CPS Energy, talk a little bit more about some projects that are going on there. Now, before I turn things over to our guest today, I just wanted to take some time to discuss a research project that we've been really excited to work on with Zpryme Networks to really study the emerging relationship between the modernization of the distribution grid and the modernization of communication networks. And what we wanted to understand is really what utilities are doing with their communication networks and how their work will evolve in the future. Now, this slide here just gives you a quick introduction to some of the research objectives, a little bit about the methodology and some of the respondent demographics. So currently we're sharing research from about 220 utility respondents, and eventually we'll get to about 350, and we'll share the final report in a few weeks. But right now we have a pretty good number of respondents, and we just wanted to share some of the research today as really a sneak peek to the report that's going to come out in a little bit. So we've had a lot of great respondents. You can see on the right-hand side of this slide, we have a great representation from a lot of different types of utilities. So that top bar there, good representation from investor-owned, municipal utilities as well as cooperatives. We also have good representation in terms of customer size. So those numbers there, looking at utility customer counts, so roughly a quarter, of the respondents have more than 2 million customer accounts. but we also have a good diversity in terms of small to mid-sized utilities as well. That last bar there really looks at the primary respondent role. So the individuals that responded, I know within utility companies, a lot of people wear multiple hats, but we asked people to say, hey, what's your primary role within your organization? And you can see there that, you know, engineering, O&M, IT, you know, a lot of these different groups that are involved with communication networks, you know, we really got some good discussion through this survey. So now let's get into some of the findings of the study. And the first couple of slides I'll walk through will really talk about communication networks both in terms of what's happening today as well as what's happening tomorrow. So on this slide, you can see that, you know, it really looks at the types of communication networks that utilities are looking at today, which is the chart on the left-hand side, as well as the types of networks that they're looking at over the next decade. And this really looks at it in terms of, you know, essentially more the ownership structure for communication networks. So today, we're seeing, you know, a lot of different approaches, but utilities are really primarily relying on multiple networks, and this is really looking at their distribution grids. The largest segment is relying on essentially both, you know, in-house as well as public networks. And we're seeing that over the next decade, there isn't, you know, necessarily a major shift in these trends. Utilities are using, you know, a lot of different networks to handle their distribution grid needs. Now, this looks at it in terms of ownership structure, but, you know, it's also important to look at, you know, what types of networks specifically are utility companies using for their distribution grid. And this slide dives into that in a little bit more detail. So we know there's a diversity of networks, and this slide really shows the types of networks. The peach-colored bar there, that's the percentage of utilities respondents who said they were using the network today. And that peachy, or the orangish, reddish, I don't know that color exactly, bar is really showing what utilities are looking at using in the next decade for their communication networks. So again, you can see utilities are considering a wide range of networks. And an important thing to note here is that these aren't necessarily, these networks aren't mutually exclusive. You know, there are a lot of different networks that utilities are using, but you know, some of these networks have different uses, and there's definitely some overlap. So for wide area networks, we're really seeing that, you know, fiber optic is the leader there. But for field area networks, we're seeing, you know, RF mesh as being a leader in that space in terms of what utilities are using today as well as tomorrow. But you can also see there are other growing areas as well. So, you know, areas like Wi-Fi as well as private cellular are growing too. So there are certainly changes going on in the marketplace, but what are utilities really noticing about their networks? And that takes us onto a slide that looks at some of the top pain points for current communication networks. And you can see that there are several areas that utilities are working through. The first is cybersecurity. I mean, that's definitely the top concern. You know, cybersecurity is something that's always evolving. You know, it's just a matter of really trying to stay ahead of, you know, people that are trying to compromise these systems. But what we're finding is that, you know, some of these older communication networks that may have been built within the last, you know, 10 to 20 years, you know, they really aren't at that stage of being prepared to, you know, help utilities handle some of these cybersecurity issues. So that's definitely a big concern for utilities. And the other areas there, really the next three areas, I really see those as concerns around the ability of utility communication networks to be able to adapt to future needs. So there are concerns about, you know, setting up and maintaining these networks, as well as obsolescence issues and low bandwidth. So there are a lot of challenges with networks as they stand today. And that, I think that really starts to get, you know, compounded by the fact that we're starting to look at this future grid that's increasingly dispersed with more distributed generation as well as distributed intelligence. So with this increasingly distributed grid, we wanted to ask utilities, well, how prepared do you feel your communication networks are for essentially that kind of distribution grid network of the future? And you can see here that about 2/3 feel, at most that their communication networks are somewhat ready, which from my work for years as a market researcher, I mean, to me that tells me that, utilities aren't feeling really ready for some of the changes that are going on. There's definitely progress that's been made, but there's certainly room for improvement. So here we're really looking to improve on the distribution network, at the edge, as the grid becomes more distributed. And we wanted to take the last few slides here to look at more of those field area networks and explore the most popular network that we saw earlier, which is RF mesh. So the last few slides here I'll cover will dive a little bit deeper into what utilities are thinking about RF mesh and how they're using it. So here you can see, we asked utilities, well, how important do you feel RF mesh is for your organization? And you can see that about, roughly 2/3 definitely felt it was an important technology, and actually have a lot of different ways that they're using RF mesh networks. So taking a little bit closer look at how they're using RF mesh networks, looking here, we asked, what are your use cases right now for RF mesh? And you can see that some of the biggest areas, AMI, SCADA, AMR, some of those big areas where you expect RF mesh to be in place. Those are a lot of really vital functions for the modernization of the distribution grid. But where does it go from here? I mean, we've talked about this need to have, more flexible, technologies and communication networks that can better adapt in the future. And this next slide takes a look at some of the top future use cases. So you can see here that again, we asked respondents to say, hey, well, if you didn't use RF mesh for AMI now, would you look at it in the future? Same with fault detection, distribution automation, demand response, those sorts of things. And you can see that there really is growth in a lot of different areas for RF mesh for utilities going forward. So definitely a lot of different communication needs. And really that need to have some flexibility within communication networks for utilities. So that's just a quick sneak peek at some of the data for this upcoming report, and just some key findings to think about as we move through the rest of this webinar. So, as we move towards more distributed resources and intelligence, those field area networks are going to continue to become increasingly important. It's critical for utilities to be thinking about what sort of flexibility they need in the future, and how to best grow their communication networks to really enable a lot of these new technologies that are coming about to be able to really integrate well into the distribution grid. It's also a important idea, again, to think about the variety of uses, what sort of use cases are coming down the road to your utility, and how are you going to best accommodate those. And last but certainly not least, really considering that security stack going forward, and how that's going to, help your organization, deliver a secure distribution network as it can. And it really challenges you to talk to your solution providers or potential solution providers, and really get a better understanding of, how they're approaching cybersecurity and, how they can really help your organizations be more secure. So that's a little bit of the research that we've been doing. We're really excited about the work we've done so far, and encourage you to keep an eye out for the full report, which will be coming out a little later this summer. So with that, I'd love to hand it over to Matt, and he's going to walk you through a little bit more about Silver Strings Networks and what they're working on. Thanks for joining us, Matt.
Great, thank you. And I wanted to thank Zpryme for sharing that great research with us. I think it's really insightful how utilities are thinking about different communications technologies and the challenges for their distribution networks. So I wanted to take just a moment and introduce Silver Spring Networks. We really see ourselves in the business of enabling the Internet of Important Things. And how we define that really is we see that as critical infrastructure devices that by their very nature require reliable and secure communications to enable various use cases for their owners and the companies that need to deploy those devices. From a Silver Spring perspective, we are very much about using RF mesh technology to enable that connectivity, and it's great to see that the research bore that out as a critical technology that companies are looking at. We provide what we call dual band mesh, which allows for meshing on two different bands, both 900 megahertz and 2.4 gigahertz, as well as providing very long range modes of up to 50 miles, kind of line of sight best case. The mesh itself is self-forming and constantly adapting. So what that means is that devices connect automatically by communicating with their neighboring devices. They establish multiple paths through the mesh for redundancy purposes. And the routes through the mesh and the mesh itself is all self-forming and automatic. It handles it in a distributed way from technology that's embedded in our communication devices themselves. So it doesn't require any operator management to manage or form the mesh. It all happens automatically. And that's one of the key advantages of mesh technology in providing very reliable and broad geographic coverage across different areas. Now from an architecture perspective, we don't just use RF mesh by itself. Typically, we combine RF mesh with other multiple network backhaul technologies. Fiber is very, very common, probably the most common, and the research bore that out for distribution automation applications. And so at the edge, devices are communicating on the mesh, but then we'll transfer to a fiber network for backhaul from the substation back to the head end. And so as the research showed, our architecture and our approach incorporates a variety of network technologies to achieve very good cost performance while creating very broad geographical coverage to ensure that all the critical infrastructure devices can be connected and managed. And through the combination of these network technologies, we can provide a higher degree of reliability than any single type of network architecture would be able to provide. From a company perspective, Silver Spring is headquartered in San Jose, California. We were founded in 2002. We have over 700 employees worldwide. Primarily today, the majority of our customers are either leading utilities or major cities across 5 different continents. We were lucky enough last year to be named a visionary in Gartner's Magic Quadrant for Managed Machine-to-Machine Network Services. And to date, we've connected over 26 million devices across about as many homes and businesses all across the world. And so we have a broad range of experience of how do we connect these critical infrastructure devices. Now, thinking about that, and today we're talking primarily about the area of our business that's focused on utilities, where we're connecting devices for grid management purposes or distribution automation purposes. We connect these devices in a variety of ways. Primarily, it's either through embedded communications in the device itself, where we actually take our comms module and embed it in the product, working together with the product vendor, and they embed that communication in the device, which makes it mesh capable. Or we have aftermarket devices called bridges, which can connect to legacy devices that are already installed in the field, either via simple serial or Ethernet connectivity. And through that range, through that methodology, we create this range of devices all communicating on a common infrastructure communications platform. Now that communication can either be peer-to-peer within the mesh between devices or back to a central location or back office application. And typically within the mesh we have takeout points that then would connect to various WAN connectivity points, either public or private, depending on the particular customer. And then that will provide connectivity to various back office applications. SCADA, DMS, OMS systems are all enabled through that type of connectivity. Now, once you have this broad range of device connectivity with applications in the back end, what is enabled is a broad range of use cases that utilities can leverage to improve grid operations. So everything from improving resiliency and reliability with FLISR-type applications, storm management, being able to optimize and make the grid operation more efficient with applications like conservation voltage reduction or intelligent volt-var control, and increasingly more and more even distributed energy resource integration for better management of the distribution grid as the percentage of distributed energy resources and renewable generation increases on the distribution grid. We also support a broad range of monitoring and analytics use cases, from load monitoring to voltage monitoring, outage detection, theft detection. All of those use cases that came up in the study, we have experience doing with customers in the field today. And those monitoring and analytics use cases will be used to get better telemetry data, have a deeper understanding of how the grid operates day to day, month to month, year to year, to drive better decision making within the operation. Another way to think about this is through the application use cases that utilities will typically deploy on our network. Typically, it's very common for utilities to start with automated metering infrastructure, and that may be installed initially for billing purposes and being able to automate meter reading. But very quickly, most of our customers learn that all of these meters sitting out at the edge of the network become a very, very valuable grid sensor. And so being able to understand outage conditions, where outages have occurred, when restoration happens, being able to understand the voltage characteristics of the network at the edge of the network are all things that the AMI system can provide for better grid management or distribution operations management. On the DA side, distribution automation side, we see our network being leveraged very broadly for connectivity of a broad range of devices on the distribution network. So switches, cap bank controllers, reclosers, line sensors are all information or all devices that are deployed to help manage the grid infrastructure itself. And so that typically will provide both telemetry information, polling of devices, getting that data back to SCADA to understand how it's operating day to day, but then also provide critical command and control functions for the management of the grid, both on an ongoing basis and during critical situations. And so we're very conscious of designing networks that can support, very low latency, high bandwidth communications for those type of devices. Now, increasingly, more and more, we're also seeing applications where distributed energy resources are also being deployed, not only from a utility grid management perspective, but also customers making decisions to install rooftop PV or EV chargers in their homes, as well as battery systems that all become, over time, we intend to become critical grid infrastructure devices. And so our network can also enable this connectivity in the home and create connectivity back-to-back office applications that will enable the understanding and the management of those assets as well as critical grid infrastructure. Now, I wanted to take just a few minutes and talk about some of the use cases that we're seeing being deployed by a few of our customers. The first one, and what we would consider probably step one, is is letting utilities be able to use the outage information that can come from smart meters to better manage outage situations. And so we see that here in the case of ComEd, where we have actually used the meters to understand when outages occur, and then as they're restored, where restoration has happened. And this has been used to reduce the overall number of outages since the smart grid was deployed, seeing improvements in both SAIDI and CAFE numbers, as well as avoiding a significant number of truck rolls. Because if you know where the outages are, where power has or hasn't been restored, you can be much more effective in where you dispatch your assets to manage those outages. And in the end, all of that benefits we've seen actually accumulate into actual improvements in customer satisfaction post-smart grid deployment versus what we would have seen it be pre-smart grid deployment. Now, step 2 is when we shift then that network capability to the distribution network. And how do you begin to automate all of the different devices that are used to manage the grid? And historically, many of these have been managed manually by dispatching trucks. But now, with the advent of these broad communication networks and cheap communications, you can actually create connectivity to these devices where you might not have had that in the past. And so we see FPL having deployed a broad range of areas, connecting devices like remote fault indicators, cat bank controllers, automated feeder switches, line sensors, all which give them greater intelligence around what's happening on the grid at any time. And we see that benefiting them in terms of specific number of minutes of customer interruptions avoided per year, 5.1 million minutes. That's a huge number, a huge difference than what they've been able to achieve in the past without these technologies. That ultimately accumulates in estimated annual OPEX savings and a huge number of avoided field visits per year, over 100,000, where they would have had to roll a truck, where now this automation has allowed them to not have to do that currently. Now, the third step that we see customers really taking is to be able to leverage this communication infrastructure for distributed intelligence in the field and intelligence at the grid edge. And what ComEd has done with their automated feeder switches is to be able to allow them to communicate with very, very low latency, typically under a second, peer-to-peer in the mesh itself. And so when there's an outage, a group of feeder switches will all communicate with one another to determine where that outage is and how power should be rerouted automatically to restore power to as many customers as possible. And all of that happens in under a second without any operator intervention, basically getting power back to customers as quickly as possible. And so this results in basically fewer customer interruptions, being able to get power back on quickly without the operator having to have any involvement. Now, once the switching is automatically done, messages are sent back to the SCADA system and the operators so they can understand what state the grid is in. So it's all done with visibility, but it speeds the reaction to these events that occur on the grid. And so that's enabled one of the key advantages of peer-to-peer technology that may not be available through other public networks is this fast peer-to-peer communication at the grid edge. Now, all of these capabilities are not useful if your network doesn't perform under critical events. And so one of the use cases that we saw recently at CPFL, one of our customers in Brazil, was that there was a tornado that went through their area, and they just happened to have Zpryme network devices deployed in that area, but they also had some legacy devices that were running on the GPRS cellular network as well. And after that critical event was over, directly after, the Zpryme devices were still all operating in the field where they had lost access to the public network. And so right at the time where you need critical operations to be able to be, it's important that that infrastructure can remain in the field and be operational during critical events. Now the fourth step here, and this is the last use case that I want to review, is really starting to show in examples of how do you leverage all this connectivity to devices, all the data that's coming back for advanced analytics use cases. And so in this case, we've had a customer, Pepco, that was able to use smart meter data to build profiles for over 5,000 transformers to identify overloading conditions. And so the benefit of this was that they were able to do some proactive maintenance or hardware upgrades in the field where those critical situations occurred before an outage actually happened. So getting into more proactive type of maintenance. The advantage of that is that there's fewer truck rolls, less things that are happening, and they can ensure that they don't end up with these unplanned outages, which are much more disturbing to customers. So finally, we implement all of these use cases with what we would consider military-grade security architecture. All of the security infrastructure has been built into our communications technology from the ground up. It was a primary consideration when we designed the technology, and there's multiple layers of security at all aspects of our system to ensure that we have a high degree of security end-to-end. And it's interesting that our experience in the field has been very similar to what the research showed as security being a primary consideration, because we've seen a lot of customers, especially on the distribution automation side, upgrade to our communications technology and replace legacy systems that did not have security or had very rudimentary security in the past. And so this is a key consideration that we've built into our network, and we've seen that proven out in the marketplace where this is a primary consideration for customers and something that they want to know that any technology they deploy today would meet, common standards. So finally, I think in summary what I would say is that Silver Spring has extensive experience in what it takes to enable critical IoT applications, including distribution automation and grid management for utilities. We've been doing it for more than a decade, and we've really built our solutions around recognized Internet standards and leveraging all the benefits and technology investment that's happened in the Internet and bringing that to critical infrastructure IoT applications like utilities. We can ensure that your devices are connected yet stringently protected. That makes it effective yet high performance, flexible yet reliable, easy to deploy, and resilient and scalable. And so I thank you for your time today, and I'll now turn it over to Fermin, one of our great customers at CPS Energy, who will tell you a little bit more about what they've done with Silver Spring's technology in their area. Thank you.
Okay. Thank you, Matt. As you mentioned, my name is Fermin Almeida. I work here at CPS Energy in the distribution SCADA. I was the technical project manager during the transition from our legacy radio system to Silver Springs. So that's basically what I want to talk about, the experience and some of the challenges that we had in deploying the Silver Springs network here in CPS Energy. The process started around 3.5 years ago. At the time, we had a lot of questions and a lot of concerns. We only had about 500 SCADA devices, and those consisted mostly of reclosures, voltage regulators, cap controllers, and those kind of controllers. We were on like I said, this point-to-multipoint radio system. So one of the concerns that we had was whether or not we would experience some large-scale outages during the cutover. If we couldn't avoid those kind of outages, how would we minimize them? Another concern had to do with convergence. We decided that we were not going to have separate relays for DA and then separate relays for AMI traffic. We were going to combine those. So the AMI and the DA traffic would be sharing relays. So was that going to cause performance issues on our DA network, which of course we expected would have priority. Another question had to do with the low device count. As I mentioned, we had about 500 SCADA devices. SSN had designed the relay network to support some 1,500 SCADA devices. So the design called for having SCADA controllers there to provide hopping points. So of course the concern was, with this low device count, was that going to cause problems? Would the mesh be viable at such low numbers? Would we be forced to pepper the service area with additional relays to compensate? So these are all some of the challenges that we were looking at when we started this. The approach that we took here at CPS Energy was to build a test farm. So we put together, we used 2 separate sites. We put a master, I should say a pair of masters at each of 2 separate locations. We put a relay in between them. We also added about 30 SCADA controllers of different types, and we put in about half a dozen meters. This proved to be extremely useful. So we were able to develop some of the failover cases that we would use in the production environment. We were able to develop the procedures to actually do the cutovers. And then we were also able to test convergence by funneling all the traffic through that single relay. One of the most important things that we found out early on is that the 2 radio systems could coexist. And that was extremely important, and it solved a lot of our problems. The service outages that we were concerned with never happened. In fact, the service outages were limited to single devices spanning about 45 minutes. And that's pretty much the time it took to pull pull the radio out and replace it with a new one and replace the antenna. The changes that were needed on the SCADA system were also completed in the same time frame. So we became pretty good at doing the cutovers, and it was seamless. From the operational side, system operators really never saw anything. They would see one SCADA controller go down, and 45 minutes later, it would pop right back up, and it was now on the mesh. The convergence issue that we were extremely concerned with turned out also not to be a problem. We ended up modifying our test SCADA system to generate a high flow of DA traffic. It was actually difficult to get the SCADA system to generate as much traffic as we needed. We also found that we were using pinging to generate the volume of AMI traffic that we needed. So it showed 2 things. At its worst, when we had the relay utilized to, I guess it was above 15%, we started noticing a drop in the DA traffic, but it was minimal. It was about 3%, 4% at its worst. We also saw that the relay behaved as advertised. It started pushing back on the AMI traffic. So that's what we expected to see. So from the meter perspective, the cost of using that relay started to go up. So again, this test farm that we used solved a lot of our problems, or helped us through moving from one system to the other. Since then, we're pretty much now on the operational side. We've expanded to about close to 1,000 SCADA devices. That's been pretty seamless and easy to do. We've noticed, of course, several improvements on the security side. All of the traffic from the CPS firewall to the endpoint radio is encrypted now. So all the data, commands, everything is encrypted. Redundancy, or the resiliency of the mesh, has proven to be excellent. Before, if a radio master got hit by lightning, we'd lose 30 or 40 devices immediately. That doesn't happen anymore. Everything simply shifts and it switches to another site. We support both near side and far side failover. And I should note, we did run into a certain issue here. Originally, when we were concerned about having service gaps that would require us to add relays, turned absolutely not to be the case. In fact, most of the controllers or most of the radios would have so many options in finding its way back to a master that we found that they were actually switching too often, and the result was momentary dropouts. So we ended up making some changes to sort of reduce their options to a more limited number. So that self-healing and self-adapting, it works both directions. On one hand, it's great because, like I said, you can lose a pair of masters and they'll simply reroute someplace else. On the other hand, if it's a perfectly clear day and everything's wonderful, they may simply decide they find another master looks better and it switches. And so you see a momentary drop as the SCADA controller goes down and then comes back up. Topographically here in San Antonio, we're pretty flat, so I think that also contributed to this issue. And like I said, it had both sides. It was an advantage and also a disadvantage in some cases. Other advantages that we've experienced with it is the direct access to the controllers. So Matt mentioned reduced truck rolls, and that's absolutely true. Before, if there was an issue or if we needed to pull logs from a controller, automatically we would have to send a truck out there. That's no longer the case. So our remote SCADA people now can remote directly to a controller, diagnose problems, reprogram it, pull data, and we don't have to send a truck out there. The round-robin scheme that we were forced to use in the past, because it was a point-to-broadcast type of scheme, that's, again, not the case anymore. So we can parallel poll, or we can use unsolicited. So the SCADA controllers can report on their own, making it a lot more efficient. Gridscape, I can't understate how great that thing is. It's because of the visibility that it gives you. I mean, at the time we were dealing, like I said, with about 500 devices, and that was difficult enough. Once you start getting to 1,500 devices, then it becomes an issue. One of the things that Gridscape lets you do is actually look into the radio. So you can see traffic flowing through the radio, you can see it coming out of the radio, going to the controller, and you can see whether or not the controller responds. Again, that reduces truck rolls, because before you'd have to send multiple crews out there, you know, the radio shop, transport shop, the remote SCADA guys, just to try to figure out what the problem is, and now you can do it remotely. And in most cases, they can fix it remotely, so they don't have to send a truck roll at all. They can simply reprogram the controller if that's an issue. It gives us two modes of methods to access the remote bridge. We can use the IPv6 or their control channel, so we can see whether or not the radio is there. That means that even if the VPN tunnel, we still have a method of reaching the radio, so we can at least eliminate the radio from problems. So use cases, we're beginning to expand. Most of them right now is DA and AMI and, of course, ODS. But now we're also moving toward fault detection and line sensors. So besides the regular bridges, we're putting stuff like GridSense out there. We're starting to deploy it. So we're moving that direction now, too. So in conclusion, the SSN mesh represents a significant upgrade to our distribution system. The enhanced security, the enhanced capability, and the increased reliability allows faster response to outages, and it makes maintaining the system much more efficiently. So all in all, it basically ends up with a better customer experience because we can respond faster to outages, and at the end of the day, that's pretty much why we're here. So that's it, Christine.
All right. Thanks, Fermin. That was great. And thank you, Matt, for your presentation earlier. That was wonderful as well. So now we have a little bit of time. We're going to go open things up, and it's your turn to ask us any questions about what you have heard today. So with that, I have a couple questions just to get things going. Fermin, a question came in for you. wanting to know, are there any use that you have for, you know, transformer sensors? And, you know, if so, I mean, what are some associated use cases around transformers?
Yes, we do. In fact, that's one of the ones that we're getting ready to deploy here, particularly in underground networks where it's much more difficult for our crews to be able to isolate problems. But measuring voltage, you know, secondary voltage at the transformers is something that we're starting to do. Not just with grid sense, but in some cases we're actually putting power quality meters out there so that we can read secondary voltages. So yes, that's another use case that we're starting to explore and implement.
Excellent. And I mean, we talked a little bit earlier in the research about, you know, some of the newer use cases that utilities are looking at. I mean, what are some other areas where you're looking to expand your communication networks that you may not be doing today?
Not so much expanding the communication network, but increased use cases. On the communication side, we're still, you know, with the mesh and in some cases fiber, but we are starting to deploy stuff like BVO and FLIZR for fault location restoration. Okay,
excellent. Now, Matt, there was a question that came in for you, and the question was: the Zpryme network, mesh network, is it end-to-end IP compliant?
It is end-to-end IP compliant. We can support both IPv4 and IPv6 addressing. The IPv6 addressing is native on the network. That's what we use for all applications. But in the case of a SCADA application where I think most SCADA systems or all SCADA systems really only talk IPv4 today, we can overlay an IPv4 addressing scheme on the endpoints so SCADA endpoints can communicate directly across the network. So yes, absolutely IP end-to-end from day one.
Matt, from CPS Energy, having both those, you know, those two networks, the IPv6 and IPv4, is extremely useful because there's a lot of things that can go wrong on the SCADA side. The VPN tunnel may not come up correctly. There may be programming issues with the SCADA system, but being able to jump on the IPv6 and ping the meter directly helps a lot.
Okay. Now, another question we had is, you know, how easy or difficult is it to really change, you know, the number of devices and sensors that are on these communication networks? I mean, what if a utility needs to connect more devices than they anticipated? I mean, how does that really work for utilities? Matt, do you want to take a first stab at that?
Sure. I mean, that's one of the great advantages of having mesh networks at the edge, is that essentially you can drop any device into that existing mesh network and it'll automatically you know, find a path home, register itself on the network, and establish its communication. And so there really isn't anything to be done other than, you know, initially registering that device in the head end and then installing it and setting it up. And so it's very, very simple and straightforward to get a device on the mesh. Now, there's additional capabilities that you can add in terms of routing of the IPv4, like we talked about, other types of network constraints that you might want to put on the particular device. So, for example, if it is a critical infrastructure device that's used for distribution automation, say a switch or something, that you want it to be able to be available at all times, even during power outages, you can also require that device to find a battery-backed route through the mesh. So we'll look for infrastructure devices that have power backup, and it will only route through those. So there are additional constraints that you can put on the device so that it has the right type of connectivity back home to the back office. But adding a new device type, is very, very simple and straightforward.
Okay. Excellent. And Fermin, do you have anything you want to add on that?
No, he's absolutely right. In fact, we ended up, while we can set the radio to find its path back to, using a battery backed up path, we actually found it was better not to. It's better to allow the radio to simply make its most efficient path back to its master, and then should something happen, if there's an outage, we've grown confident enough with the system's ability to adapt that it will switch back and use a higher cost battery backed up path if it needs to. So we have that confidence now that we allow it to just connect however way it wants to connect back into the system.
Okay, that makes sense. Another question, I think we had a couple of questions around this, are just the interoperability of communication networks. I think during my presentation there was a question that came up around, challenges of current communication networks, and we definitely saw in the research that utilities, are using different communication networks. So, I mean, how do utilities really work through that interoperability piece? Is it a challenge? Is it? I mean, what are some of the recommendations that you have? And Matt, if you want to jump in there for that one, that would be great.
Yeah, sure. I think there's two parts of this communication as I look through some of the questions that came over. First is basically making sure that you design the right architecture for the right problem. And so Silver Spring spends a lot of times with customers up front to understand what their use cases are, not only the ones that they're going to be deploying, from day one, but what might be coming in the near future, the next couple of years, and making sure that we design a network infrastructure to be able to support that. So, and that can be very simple in terms of one use case, a network that you might go deploy for automated metering initiatives, or you might have a network that's doing AMI, distribution automation, street lighting, as well as distributed energy resource integration. And so all of those use cases are accounted for in the network design. We think about what backhaul technologies will be utilized. Perhaps there's multiple backhaul technologies utilized for one set of devices that may not have such critical demands on them like a metering, but switches and cat band controllers and reclosers may be communicating via another backhaul technology, and that's all part of a common network infrastructure that we would design and deploy. And then we need to make sure, having everything on our end be IPv4 or V6 certainly makes that interoperability a lot more straightforward, but we also have to think about the security overlays that are put on that end-to-end. And so we design all that up front, we make sure we know how we're going to go deploy it, and then we go execute it. Another question that was raised was really around how do you manage the transition from a legacy network technology to a Silver Spring network technology. And this is especially important with critical infrastructure devices. And we've worked with a lot of our customers, ComEd probably being the example that comes to mind, who had a legacy mesh technology deployed that they were replacing. And we actually worked with them to understand the routing of the existing network and design the order of replacement such that we replaced the network devices, the legacy network technology, from the outside in, so to speak, so that we didn't orphan any devices as we were transitioning from one technology to the next. And so the downtime was essentially what it took to unplug one device and plug another communications device in. And so that was all part of the design and the deployment strategy. We worked together with the customer to go design to minimize or actually almost nearly eliminate any downtime of any single device that would occur in the transition between technologies. And so we have some broad experience in doing that with multiple customers.
Yeah, those are some great recommendations and examples. I mean, Fermin, what are you seeing in that space around interoperability? Have you had any issues or things that you're working on around that, or has it really not been a problem for you at this point?
It really hasn't been a problem to us at this point. We've not really had interoperability issues. We have the radio mesh that handles the majority of our traffic. The bridges are flexible enough for talking to different controllers, some of the legacy controllers that are stereo only. Some of the new ones we're switching over to Ethernet. And in some cases we're still using fiber. Most of our masters, well actually all of our masters have hard connections back to the IPv6, IPv4 network. So no, I mean at this point everything seems to be working the way we wanted it. It is important, like Matt mentioned, that you work out a strategy that minimizes the downtime when you're going to do the transition from one system to the next. So at least from the RF perspective, you do need to make sure that those two systems can coexist when you're doing the, you're migrating from one system to the SSN mesh.
Okay, that makes sense. So we just have a couple of minutes left here, and I just wanted to hear from each of you what your recommendations are for utilities as you kind of move to these more distributed grid infrastructure or more distributed distribution networks, and some of these newer resources that are coming online. Around energy storage, electric vehicles, all of these areas. I mean, what should utilities be keeping an eye out for, as they look to communication networks to help address these areas? I mean, Fermin, what would be some of your recommendations?
Well, I'm not really sure if I have any specific recommendations. I mean, we're in the position right now where we transitioned, like I said, from this legacy radio system with very limited capabilities, very limited bandwidth, to this much higher bandwidth, much more capable mesh. What we're discovering, is the fact that we haven't run into anything that we can't implement. Some issues came up about, adding some of this underground transformer sensing, and we were able to pick up a product that is Silver Springs compatible and started testing and deploying. So, I mean, we're in a position right now where a lot of this new use cases that are being introduced, we're in a position where we can take advantage of it.
So having that flexibility seems important. That's
probably more critical because everything changes and everything changes really quickly.
Yeah, definitely. And Matt, how about you? What are some of your recommendations for utilities?
Yeah, I think the number one thing is thinking about the network as a platform and making your choice of network really as you would any other platform decision within your utility infrastructure. That includes thinking about all the use cases that you need to support today, but what you think may be coming in the future. And you guys mentioned a few of those, which are definitely, I think, on the minds of a lot of utilities in terms of how do we connect distributed energy resources, PV, battery systems, other types of devices there, EV chargers, and making sure that your choice of network is going to be able to support those use cases, not only in terms of providing communication to the head end, but also supporting distributed intelligence. And while most utilities aren't doing a lot with distributed intelligence today, because these communication platforms is an investment you're going to make for many years, it's going to be with you for a long time, ensuring that those platforms are capable of that peer-to-peer communication, of enabling that distributed intelligence is going to be really important. And we're already seeing applications where having some type of processing capability at the edge, and Silver Spring is now doing pilots with kind of Linux compute environments that can sit as part of the communications infrastructure at the edge of the network, as being critical to enable connectivity of these devices, even things as simple as protocol conversion but also being able to ultimately have distributed intelligence that's sitting out at the edge of the grid and be able to make command and control decisions in an automated way based on telemetry data that's collected from a variety of devices. Maybe you're getting some information from meters at the edge of a feeder, you're combining that with transformer loading information, then communicating instructions to a smart inverter to raise or lower voltage. All of these things are coming in the near future, and making sure that the grid infrastructure that you choose today, the communications infrastructure that you choose today, can support those application use cases in the future.
Excellent. Those are great recommendations, and a lot of things for utilities to be thinking about. So we are just out of time. Matt and Fermin, thank you so much for chatting with us today. We really enjoyed the conversation. I'm going to turn it back to Aaron Otan to close things out.
Thanks, Christine, and thank you so much to Matt and Fermin for taking the time to chat with us today. We really appreciate it. And as a quick reminder, everyone attending today's webinar will receive an email with links to the webinar presentation deck and the webinar playback. And if you have any other questions, you can always reach us at info@zpryme.com. Thanks again to Silver Spring Networks for presenting this webinar, and from all of us at Zpryme, thank you for being part of today's webinar. We hope you have a wonderful Tuesday. Goodbye.